Okay, hello everybody. I'm going to talk about a new modulation format for short-haul communications that can be used over multi-mode or multi-core fibers. We call this format mode vector modulation because it is an extension of Stokes vector modulation, but for multi-mode and multi-core fibers. I would like to acknowledge here the contribution of my co-workers at Montana State University, Jarek Wapis and Eric Fink. Here is an overview of my talk. I will go through the basics of the modulation format in the beginning, and then I'm going to discuss about the transceiver architecture, how we optimize the constellation in the generalized Stokes space, and how we did the bit to symbol mapping, because gray coding is not possible. And finally, we calculated the performance of the optically preamplified direct detection receiver. So you all know that optical interconnects for inter-data center networks must meet some requirements, especially low cost, but also low energy consumption and high spectral efficiency. Now, for low cost, people consider direct detection because in this space, coherent detection is considered for the moment prohibitive. In order to increase the spectral efficiency, people try to go away from intensity modulation direct detection, at least the binary part. They try PAM4, but as you know, this is a type of modulation that is one-dimensional. In order to spread points more, we want to go into higher dimensions. So Stokes vector modulation uses the X and Y polarization degrees of freedom in single mode fibers jointly to increase the dimensionality of signal space. It actually spreads the points in the three-dimensional Stokes space. And the advantage of using Stokes vector modulation, of course, is that the state of polarization can be measured with direct detection receivers. So we want to extend this idea in order to use multi-mode and multi-core fibers that have a higher dimensional Stokes space and at the same time use direct detection. Okay, here is a typical multi-core fiber. Without loss of generality, I will assume that we have a homogeneous single-mode core multi-core fiber. But what I'm going to discuss applies also in multi-mode fibers as well as in free space propagation with orthogonal mode sets. So you have a number of cores at your disposition. You can select a subset K of cores and launch multiple electromagnetic waves in the X and the Y polarization. Here you see only the electric wave in its degree of freedom. And although I made here all the waves to have the same amplitude and the same initial phase, you can play with that. These are design parameters. And like that, you can create spatial modulations that will turn out are very energy efficient, but you are going to pay in spectral efficiency and complexity. Okay, here are the waves from the previous picture over the K cores. And we can write the amplitudes and the phases in a generalized Jones vector. And then we can go into the Stokes space because this vector is complex and cannot be measured directly with direct detection, only with coherent detection. I want you to notice that the Jones vector has n complex components, and these components depend on 2n real parameters, the amplitudes and the phases. Okay, the Stokes vector is this quadratic form where lambda denotes the Gell-Mann matrices. And there is a normalization constant to make it into a unit vector. Now it turns out that this transformation gives us n squared minus 1 real components. Again, n is 2 times the number of cores because we have X and Y polarization in each core. However, notice that these components still depend on the original 2n real parameters, so they are interdependent. And this makes the generalized Stokes space to have a Poincaré sphere that is not fully covered with valid vectors. Okay, we can measure the Stokes components again using a direct detection receiver. Actually, we'll use a transmitter that materializes the Jones vector, and we'll use a receiver that detects the equivalent Stokes vector. So here is an implementation for a 2 single mode core multi-core fiber, which you can see here. And this contraption in the front is to create the Jones vector. So remember, the Jones vector has n components, so we need n branches. We split the light from a semiconductor laser using electro-optic splitters here in the various branches, so we can control the amplitude, and we can control the phase using phase modulators. And then the remaining part is polarization controllers and polarization beam combiners in order to inject the light in both the X and Y polarization of each core. Going to the receiver, we first optically preamplify the signal, and then we have a matched optical filter in order to reject as much as possible out of band noise. And now you have to realize that the Stokes receiver actually is an interferometric receiver. So what it does is it takes pairs of components of the electric field and interferes them by making a superposition and taking the square modulus if we assume that the photodiode is an ideal quadratic receiver. So we need a bunch of splitters, couplers, polarization controllers, and polarization beam splitters to create these pairs. And because the Stokes vector has n square minus 1 components, we need n square minus 1 branches. Actually, because each branch will have a balanced pair of photodiodes, we need twice as many photodiodes as branches. So you can see that the complexity goes up quadratically. That's the drawback of this modulation format. However, we believe that it can be viable if we have optical integration at the transmitter and the receiver. Now I want to discuss about the remaining parts. We digitize the signal. We have a rudimentary DSP circuit that follows the rotations of this mode vector. We cannot counteract modal dispersion when we have direct detection because we lose the phase information, but we can counteract mode rotations, like we can counteract polarization rotations in Stokes vector modulation. And then we have a decision circuit that is basically an implementation of a maximum likelihood criterion, assuming that all the transmitted signals are equiprobable. Okay, now regarding the signals that we send into the different modes, what should they be? Well, they should be spread out on the Poincaré sphere as much as possible. Okay, here is the case of SVM. We have a single mode fiber with 2 spatial degrees of freedom. And these 2 modulations were proposed by Kikuchi in an original paper on SVM in 2014. The reference is in the paper. I didn't have space to write it here. So he proposed a constellation with 4 points. It's a simplex, and then a constellation with 8 points that is a cube inscribed in the Poincaré sphere. But if you want to have an arbitrary number of points, for example, 256 points on the Poincaré sphere, this is not a trivial problem. Actually, mathematicians are trying to solve this for about 100 years. There are exact solutions for the 3-dimensional space. There are not exact solutions for higher dimensional spaces. Plus, in our case, because of this transformation that I showed you before, there is only a manifold of 2n parameters over which the valid Stokes vectors lie. So here is what we found using the method of steepest descent and using the equivalent electrostatic potential as our proxy for minimizing the error probability. Actually, what we did is we generalized the Thomson problem. If you are familiar with electrostatics, the Thomson problem is the following. If you have equal charges on a conductive sphere and you let them relax, they will try to relax at positions that are as far as possible from each other. So we applied this to the manifold of valid states in the Stokes hyperspace. So we find this, for example, for a 2-core multi-core fiber and 256 points. There are no hypercubes because due to the interdependence of the Stokes parameters, you cannot find a cube. There are simplices because simplices are allowed, and actually you can calculate the coordinates of the points analytically. You can see more about this work on a paper that we are going to present in the IEEE Photonics conference next month. Here is one of the signals from a constellation. It's the constellation with 8 spatial degrees of freedom and 64 points. So you see here the illumination of the 4 cores, which have 8 degrees of freedom, X, Y polarization each. You see here only the intensity pattern. There is a phase difference in the launch signals, but you cannot see it here. Okay, now how are we going to do bit to symbol mapping? Gray coding is impossible. Let's see why. Let's take an example. Again, the 2-core multi-core fiber, 4 spatial degrees of freedom, 32 points. Actually, for this particular constellation, there are published results by other groups because obviously this problem is interesting in quantum mechanics as well. In order to show you how the constellation looks, I will make a graph. Since we cannot visualize the graph in the hyper Stokes space. So here are the 32 points. Now, if you do optimization, as I explained before, you find a lattice that seems to have 2 groups of internodal distances. So there are nodes that are close together. Actually, here are in total 343 closest neighbors, and then there are nodes that are further apart. So if we draw just the closest neighbors as edges, you find this very well-connected graph. Actually, if you see the vertex degree in this graph, you see that about 21 edges per average emanate from each node. So since you have only 32 points in the constellation, obviously you cannot do gray mapping. So gray mapping is impossible, but this is a combinatorial problem. Actually, if you take 32 factorial here to label the nodes, you will have 10 to the 35 combinations. And for this type of combinatorial problem, simulated annealing is good enough. So that's what we used. And again, we'll present the results next month. You find this type of mapping of bits to symbols. Okay, with these 2 things now, the important thing is to calculate the error probability. So for the bit error probability, we use the union bound and we calculated it in closed form. This is a very beautiful calculation. It's not in the paper. It will be presented in JLT soon. Just to give you an example, here we have the results of this analytical formula for the bit error probability as a function of the bit signal to noise ratio. You see here only the results for simplex constellations, as the dimensionality of zone space varies from 2 to 16. You see that for simplex constellations, the larger the dimensionality of the space, the better, because the Euclidean distance increases with the dimensionality. Okay, we can take the results from the previous graph and map them on here. Here you see the spectral efficiency on the y-axis and the bit signal to noise ratio in order to achieve a specific error probability. So let's assume that our FEC corrects a error probability of 10 to minus 4. If you use only simplex constellations. SVM gives you this performance, but if you increase the dimensionality of Stokes space, you can gain, just by going from 2 to 16, from a single mode fiber to an 8-core fiber, you gain 6.6 dB, and this continues to increase, but of course the complexity increases quadratically, and also, as you see, the spectral efficiency falls slightly. So to summarize, in this talk I proposed a new modulation called mode vector modulation. It has high energy efficiency compared to Stokes vector modulation, and since Stokes vector modulation has high energy efficiency compared to PAM, it is better for short-haul communications. It uses spatial degrees of freedom. It's a spatial modulation. Here we studied the transceiver architecture, the geometric constellation shaping, the bit to symbol mapping, and the performance of the optically preamplified direct detection receiver. And we showed that we can improve dramatically the SNR performance, but at the expense of the transceiver complexity and slightly of the spectral efficiency. So in the future, someone has to study the fiber transmission effects and their compensation using DSP. Before I close, I would like to acknowledge our sponsor, the NSF, for this work, and also announce that we recently received a generous award from the Air Force Research Lab. This is to build a hybrid classical quantum network in the MSU campus in Bozeman, Montana. You see it here. And if you are interested in a collaboration or working in this project, please contact me. Thank you for your attention.
Thank you for the presentation. Maybe start with the, you have this 4-dimensional space with 256 constellation points, and you said that this problem is very difficult, that people have been working on this problem for a very long time. Can you say one more time what the problem is?
Yes, the problem is to uniformly space points on a sphere. Actually, in the 3 dimensions, if you use Mathematica, for example, there is a simple command called sphere points that can give you approximately equidistant points. But when you go to higher dimensional spaces, the problem is more difficult. And here, our problem is also, if we go back, okay, here, the problem is that we have a Stokes vector that covers only part of the sphere. So it covers a manifold in the n²-1 Stokes space. And to uniformly spread points on the manifold, this is an unsolved problem.
But numerically, this is completely doable, isn't it?
Of course. So you used the method of steepest descent, and we used so normally you have to minimize the error probability, but because this is computationally intensive, even if you use the union bound that I showed before, we found a proxy for the optimization function. So we assume that we have an electrostatic potential and we want to minimize the potential by spreading the points on a conductive manifold. So this works well. Simply, as usual, with methods like steepest descent, you have to find a good original starting point and then iterate. That's again not obvious, because then it means you have to approximately uniformly distribute and then let the steepest descent to do it. It is a challenging problem if you go to multidimensional multi-core fibers. So we did it for relatively small n's and m's. Okay. But it is doable, yes.
Okay, thank you. And I have a second question on the union bound of the bit error rate slide. Maybe I misunderstood it, but did you say that you have, or you are about to publish a new expression on this?
Yes, the union bound for Stokes vector modulation and for polarization shift king is published. However, the generalization in the higher dimensional Stokes space is non-trivial. It requires, I don't know, about 30 pages of calculation, and we are going to publish this calculation.
Right. How is this different from union bound on a multidimensional Gaussian channel?
So basically, when you square Gaussian noise, we assumed we have Gaussian noise from the amplifiers, you get non-central chi-square distributions if you have the signal as well. Now, if you have these multidimensional chi-square distributions to find an analytical expression, is a little bit challenging, but eventually when you do it, you realize, okay, finally this expression is not so much different than, let's say, DPSK, MDPSK, all the receivers that are interferometric, and they are direct detection. But it is not obvious what is the difference if you don't do the calculation. So you're welcome.
Vectors as the number of Stokes components, right?
Right.
No way to reduce that number? Stokes vectors,
Actually, there is a way. Thanks for asking, because I forgot. So you see, the thing is, out of all these n square minus 1 components, they are interdependent and they depend on two n real parameters. So you can reduce the complexity of the receiver to a linear degree. So the complexity doesn't increase quadratically, but linearly, but yet this is another paper. So, but it is feasible. You're welcome.